So, welcome students for the chemistry lecture. And last time you have studied the derivation of kinetic gas equation, assumptions of the kinetic gas theory, and now you are going to learn the ideal gas laws. At first, we will see what is the Boyle's law. Here, the Boyle's law is one of the law in a physics chemistry that concern the behavior of gases. When gas is under pressure, it takes less place, and at the higher pressure, the smaller is the volume. That means, in short, the Boyle's law tells us about the relationship between volume of the gas and its pressure at a constant temperature. The law states that at constant temperature, the mass of given gas or uh, gas of definite mass at constant temperature, its pressure is inversely proportional to volume. In short, for a definite mass of a gas at constant temperature, its pressure is inversely proportional to volume, or the product of P pressure and volume is constant at constant temperature. This is the Boyle's law. Then you have studied the difference between ideal gases and real gases. We revise the difference between ideal and non-ideal gases or real gases. All of you know, ideal gases obey all gas laws at all conditions of temperature and pressure. And here, all gas laws means ideal gas laws, and that laws are Boyle's law, Charles' law, Avogadro's law, Graham's law, etc. And the real gases or non-ideal gases, they do not obey the ideal gas laws, and real gases, they obey gas laws only at low pressure and high temperature condition. Then the second distinguishing point in between ideal and non-ideal gases, it is the volume occupied by the molecules of a gas is negligible as compared to the total volume occupied by the gas, and the volume occupied by molecules is not negligible as compared to the total volume of a gas in case of real gases, because real gases are rigid and incompressible bodies. So we cannot neglect the volume occupied by real gas molecules as compared to the total volume of the gas. Then the next distinguishing point here it is the force of attraction among the molecules are negligible. There is no any kind of force of attraction exert in between the gas molecules in case of ideal gases, but in case of real gases, the force of attraction are not negligible at all temperatures and pressures. And the ideal gases, they obey the ideal gas equation, and all of you know the ideal gas equation is P it is equal to nRT, where N it is the number of moles of the gas, R it is the gas constant, T it is the temperature, Phi it is the volume of the gas, and P it is the pressure. In short, the product of pressure and volume of any gas, it is equal to RT for 1 mole of gas. This is the general gas equation. It is obeyed all ideal gases. And the real gases, they obeys the van der Waals equation. And in the next point, here you have to learn, or you will be able to derive the van der Waals equation. Time being, simply remember the van der Waals equation, it is equal to P plus A into N square upon phi square into phi minus NB, it is equal to nRT. As usual, this N, it is the number of moles, phi it is the volume, P it is the pressure, and A it is the van der Waals constant, and here again B it is also another van der Waals constant, R it is the gas constant, and T it is the temperature. We will derive this van der Waals equation in the next point. Then see the Charles law. Here the volume of given mass of gas varies directly as its absolute temperature provided the molecule of gas, that means moles, and pressure is kept constant. Then the Gay-Lussac's law, the pressure of gas varies directly as its absolute temperature, provided the moles and volume is kept constant. Then Avogadro's law, here for a given mass of a gas, an ideal gas, the volume and amount of the gas are directly proportional if the temperature and pressure are constant. That means the gas obeying Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, all these gases are called as ideal, and the real gases, they shows the deviations from the Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. We will see the deviations of real gases from the Boyle's law here. The behavior of real gases, that is the deviation from the ideal gas behavior, or the deviations of real gases from the ideal behavior. Here, the PV values for ideal gases are constant at constant temperature, and this is the plot of here PV upon RT versus P, and this PV by RT, this ratio, it is constant for ideal gases. This is the straight line parallel to the x-axis. This is for ideal gases. While the real gases, they shows the deviations from the ideal behavior. That means for real gases, at first this decreases with increase in pressure, reaches to the minimum, and then increases with increase in pressure. Here the deviation of real gas from Boyle's law, that is the PV value decreases after an increase in pressure, reaches to a minimum value. That minimum value, it is the characteristic of gas. After the PV value starts increasing, the curve then crosses the line for ideal gas, and after that shows the positive deviation continuously. That means these PV values are greater than the ideal gas PV values. Here, it is thus found that real gases do not follow ideal gas equation perfectly under all conditions. And remember, real gases, they obey ideal gas laws at low pressure condition and high temperature condition. But as pressure increases, the real gases, they shows the uh, large deviations from the ideal behavior. Then this is also the graph of PV versus pressure values. That means the product of pressure and volume, it is taken on the y-axis, and the pressure values are taken on the x-axis, and this is the graph of CO2 gas. Here, in case of CO2, the Pv values at first decreases with increase in pressure, reaches to the minimum and then increases with increase in pressure. Okay, at high pressure here, the all gases they shows the large deviation from the ideal behavior. And all of you know, in case of ideal gases, the Pv values are constant at constant temperature. Then this pink line or pink curve, it shows the deviations of N2 gas. In case of N2 gas also, the Pv values decreases then increases with increase in pressure, and in case of H2 gas, the Pv values are greater than the Pv values of ideal gas. Okay, and in case of H2 gas also, the Pv values increases with increase in pressure. This is the this graph, it shows the deviations of real gas from Boyle's law. In case of Boyle's law, the Pv values are constant, and this dotted line, it is for the ideal gas behavior. And in case of real gases, CO2, H2, N2, instead of getting this straight line, we get a curved lines. And in case of real gases, the Pv values first decreases, reaches to the minimum and then increases. This is the deviation of real gases from Boyle's law in case of CO2, H2 and N2 gas. Then we will see what is the Boyle temperature. Here the temperature wherein the properties of real gas coincide with those of the perfect gas. That means the temperature range at which the real gases they behaves ideally within the that temperature range. Then boil temperature can also be defined as the temperature where a real gas obeys the ideal gas laws over an appreciable pressure range. Then deviations of compressibility factor, that is Z, from unity are positive when the gas is above the boil temperature, and below the boil temperature the value of Z decreases below unity before approaching it again and increasing above 1. This is the graph which shows the deviation. Here the boil point temperature. Here in case of CO2 gas, the Pv values or Z factor, it decreases, reaches to the minimum and then increases. This is the graph for N2 gas, this is graph for H2 gas at a different temperatures. Then see here the effect of temperature. This is the curve of N2 gas for different temperature. The first curve, it is for 203 degree Kelvin. The second curve for 283 Kelvin. The third graph for 248 degree centigrade temperature, and the last graph, it is for 323 Kelvin temperature. These curves in the figure represent Pv values for nitrogen gas at a different temperatures ranging from 203 degree to 323 Kelvin. From the above figure, it is clear that as temperature increases, the dip, that means the decrease in Pv value curve, becomes smaller and smaller, and the position of minimum moves to the left hand side. Okay, then the boil temperature here. Boil temperature at a certain temperature, in this graph the temperature is 323 Kelvin. The product Pv is constant over an appreciable range of pressure. Within this range, gas obeys the Boyle's law. This temperature is known as Boyle temperature or Boyle point. The Boyle temperature, below the boil temperature, Pv value first decreases with increase in pressure, goes through a minimum and then increases, and above the boil temperature the product Pv increases continuously. Hydrogen and helium have very low boil temperature, and that is the 108 Kelvin and 53 Kelvin. That means the boil temperature of hydrogen gas, it is 108 degree, and for helium gas it is 53 Kelvin respectively, while the nitrogen and other gases have higher boil points. Similarly, the more easily liquefiable gases have high boil points, while the gases which are difficult to liquefy have a very low boil points or boil temperature. Once again, I repeat, what is the boil temperature? It is the temperature at certain temperature, in this case of nitrogen, that temperature is 323 Kelvin. The product of Pv is constant over an appreciable range of pressure. See, this is the graph. The product of Pv at this temperature 323, it is constant for appreciable range of pressure. Within this range, the gas obeys Boyle's law. Within this pressure, the nitrogen gas obeys Boyle's law, and this temperature is known as Boyle temperature or Boyle point. Then the gases which are below the boil temperature, their Pv value, their Pv value sorry, first decreases with increase in pressure, goes through a minimum and then increases, and the gases which are above the boil temperature, their product of Pv increases continuously. In case of H2 gas and helium gas, already you have seen this. And the easily liquefiable gases have high boil points, and the whose boil temperature is less, they are not easily liquefiable gases. That means the easily liquefiable gases have high boil points, while the gases which are difficult to liquefy have a very low boil points. Then we will see the deviations of Charles' law. According to Charles' law, the pressure remaining constant, the volume of given mass of gas increases or decreases by 1 upon 273 of its volume at 0 degree centigrade. I repeat once again the Charles' law. According to Charles' law, the pressure remaining constant the volume of given mass of a gas increases or decreases by 1 upon 273 of its volume at 0 degree centigrade temperature or 273 Kelvin for every degree rise or fall in temperature. If Vt is the volume of gas at temperature T and V0 is the volume of gas at temperature 0 degree centigrade, then the Charles law can be represented mathematically as here Vt it is equal to V0 in a bracket 1 plus alpha T, where alpha is the coefficient of cubical expansion. For gases obeying Charles' law, the value of alpha should be less and its value is 1 upon 273 and this ratio becomes 0.00366 at all pressures. Non-ideal or real gases obey this value only at low pressure and at relatively high temperature. At high pressure, there are considerable deviations from this value. The most easily liquefiable gases like CO2, NH3, HCl, CH3Cl, etc. shows the large deviations. Okay, then we will see the deviations from Avogadro's law. According to Avogadro's hypothesis, the volume occupied by 1 mole of every gas have a volume that volume should be 22.414 liters or 22.414 decimeter cube in SI unit, and it shows it should be independent of nature of a gas, and ideal gases obey this value. That means every gas every gas 1 mole volume of gas it should be this much 22.414 decimeter cube, and real gases they shows the either increase in the volume or decrease in the volume of 1 mole of gas. Then the non-ideal gases shows deviations from this value, that is volume occupied by 1 mole of these gases at NTP it is not exactly equal to the 22.414 liters or decimeters cube. And remember, the most easily liquefiable gases shows the larger deviations. That means their volumes are greater than 22.414 liters. Then the next point, causes of deviation from gas laws. And as last time I have told you, the gas laws were derived from the kinetic theory of the gas, and following two assumptions, they are not obeyed by the real gases, and that two assumptions are the actual volume of the gas molecule is negligible in comparison with the total volume, and the gas molecules there is no intermolecular force of attraction in case of ideal gases, but in case of real gases there is a intermolecular force of attraction, and these two are the main reasons behind the real gases they shows the deviations from the ideal law. In detail we will see the causes of deviations from gas laws, and we will derive the real gas equation or Wonderbox gas equation next time. Thank you. Thank you for your patient listening.